In the last lecture video, we saw how to construct the principal components from a known covariance matrix. Looking back at example 5, this was the last example that we looked at in the last lecture video. And so we're given that we have a multivariate normal distribution of rank 3. Here is the known covariance matrix. It's a 3 by 3 positive definite matrix. And from this, we were able to determine the coefficients that we can use to calculate the principal components from the original variables. We were able to determine the characteristic roots, which give the variances of the principal components. In fact, on the next slide, this is the information we have. So the characteristic roots of cap sig were lambda 1 equal to 22.74. That's the variance of the first principal component. Lambda 2 is 14. That's the variance of the second principal component. And then lambda 3 was 11.26. That's the variance of the third principal component. Now, how do we construct the principal components from the original three response variables, x1, x2, and x3? Well, we apply the appropriate coefficients to get that principal component. So, for example, C1 is the length 1 characteristic vector of cap sig corresponding to the first principal component. C2 is the length 1 characteristic vector of cap sig corresponding to the second largest principal component. And then C3 is the length 1 characteristic vector of cap sig corresponding to the third principal component. And so if the response vector again is bold X, where it's a 3 by 1 random vector containing the random variables, x1, x2, and x3, then this is how we would construct the principal components. So the first principal component, which we're denoting by y1, would be obtained from the original 3 response variables by using these coefficients. All right, so 0.54 times x1 plus 0.64 times x2 plus 0.54 times x3. To get the second principal component, we would apply these coefficients in C2 to the original variables. And so y2 would be 0.71 times x1 plus 0 times x2 minus 0.71 x3. And likewise, to get the third principal component, we would apply the coefficients in the third characteristic vector. And so the calculation, or the way we would construct the principal component from the original 3 variables, is according to this linear combination here. In addition, the variances of the 3 principal components are given by the 3 characteristic roots of cap sig. Now, in actual experimental situations, the population covariance matrix is not going to be known. And so we're not going to be able to compute the actual principal component coefficient vectors nor the principal component variances. If we don't know cap sig, then we cannot do calculations with it. We cannot extract the characteristic roots nor the characteristic vectors. Now, we can estimate these quantities, however, by performing principal component analysis on the sample covariance matrix, which, if you'll remember back to our discussion when we talked about estimating the parameters of a multivariate normal distribution, we talked about how to estimate the population covariance matrix using data. And we denote that sample covariance matrix or estimated covariance matrix this way. So we put a hat on it, and that indicates that it's the sample covariance matrix, and in particular that it's the unbiased version of the estimated covariance matrix. You'll remember that we had two potential estimators for the covariance matrix. The first one we looked at was based on maximum likelihood estimation, and we showed how to calculate that, or at least described it. But we also pointed out that that estimator is somewhat biased. It's biased low, in the sense that the estimated variances tend to be a little bit too small. And so we did the adjustment that we've discussed to make that the estimate of the covariance matrix unbiased, and that unbiased version has the hat on it. And we call that the sample covariance matrix. So we don't know the true population covariance matrix, but if we have a random sample from the population, then we can use that data to estimate the population covariance matrix and then use the estimated covariance matrix in our analysis. And it's from that estimated covariance matrix that we get our estimates of the principal components and of their variances. So in general, a statistical inference is based on the estimated principal components computed from the sample. So how do we do this? Well, let x1, x2, and so forth up to x sub n. And by the way, you can see that these are bolded, so you know that I'm talking about vectors. Each of these are p by 1 vectors. So let bold x1, bold x2, and so forth up to bold x sub n be a random sample from a multivariate normal distribution with mean vector mu sub x and covariance matrix cap sig sub x, both of which are unknown. The characteristic roots and length 1 characteristic vectors are unknown because we don't know cap sig, and therefore they must be estimated. So let's use the data we have. Let's use this random sample of vectors from this multivariate normal distribution to estimate the mean vector as well as the covariance matrix using the data. Now, once we have the estimated covariance matrix, the sample covariance matrix, we can extract the characteristic roots of that estimated covariance matrix, and to help us to remember that those characteristic roots are estimates of the characteristic roots of the true covariance matrix, we will put hats on top of those lambdas. So that just reminds us that these are the characteristic roots not of cap sigma, because we don't know cap sigma. These are the characteristic roots of cap sigma hat. All right, in addition to extracting the characteristic roots from the estimated covariance matrix, we're going to find length 1 characteristic vectors of the estimated covariance matrix corresponding to the p characteristic roots. So this is how we're going to estimate the characteristic roots and the characteristic vectors of cap sig, and from these obtain the estimates of the principal components and the estimates of the variances of the principal components. Then once we have obtained the estimated characteristic roots and estimated characteristic vectors, from which we can calculate the estimated principal components, we're going to apply these coefficient vectors to the data in our random sample, and we're going to calculate estimated principal components for each of our experimental units. So you can see here that the data consists of a sample of size n, and so we have p response variables that are measured, that have been measured on n experimental units. And so for each experimental unit, we're going to calculate the principal components, the estimated principal components, based on their own data. And so that's what's described on the next slide. So the estimate of the kth principal component for the rth experimental unit is calculated according to what we've been talking about. We apply these coefficients, we construct a linear combination of the original variables based on the coefficients contained in the appropriate characteristic vector. And we're going to do this for each experimental unit. So each experimental unit brings its own data into the data set, and for each experimental unit, we compute its own, the values of its own estimated principal components. And so that's what essentially what this slide is telling us, that each experimental unit is going to have calculated the values of its own estimated principal component values. All right, so the next slide gives us a couple examples to look at. I'm not going to look at these examples right now. I'm going to go to a different example that I think that I typically start with. And so we're going to look at that right now. And so let me bring up the data, and bring up a program, and bring up a description of this data. By the way, this data comes from one of the recommended textbooks, the recommended textbook written by Brian Manley. Now, this is a description of the example and the data set. This is example 1.1 from Manley's book, and the data are contained in table 1.1. And so, and I think this is a very interesting data set, a very interesting example. So, after a severe storm on February 1st, way back in 1898, a number of moribund sparrows were taken to Herman Bumpus's laboratory, biological laboratory at Brown University in Rhode Island. Subsequently, about half of the birds died, and Bumpus saw this as an opportunity to see whether he could find any support for Charles Darwin's theory of natural selection. To this end, he made 8 morphological measurements on each bird and also weighed the birds. The results for 5 of the measurements are shown in Table 1.1 for female birds only. From the data that he obtained, Bumpus concluded that the birds which perished not through an accident, but because they were physically disqualified, and that the birds which survived because they possessed certain physical characters. Specifically, he found that the survivors are shorter and weigh less, have longer wing bones, longer legs, longer sternums, and greater brain capacity than the non-survivors. He also concluded that the process of selective elimination is most severe with extremely variable individuals, no matter in which direction the variation may occur. It is quite as dangerous to be above a certain standard of organic excellence as it is to be conspicuously below the standard. This was to say that stabilizing selection occurred so that the individuals with measurements close to the average survived better than individuals with measurements far from the average. In fact, the development of multivariate statistical methods had hardly begun in 1898 when Bumpus was doing his analysis and his writing, but it's amazing that he was able to come to these conclusions, and it shows just how sharp of an individual he was. Now let me continue on here. So the correlation coefficient as a measure of the relationship between two variables was devised by Francis Galton in 1877, so not too much previous to when Bumpus was doing this analysis. However, it was another 56 years before Harold Hotelling described a practical method for carrying out a principal component analysis, which is one of the simplest multivariate analyses that can usefully be applied to Bumpus's data. Bumpus did not even calculate standard deviations. Nevertheless, his methods of analysis were sensible. Many authors have reanalyzed his data and, in general, have confirmed his conclusions. Taking the data as an example for illustrating multivariate methods, several interesting questions arise. In particular, how are the various measurements related? For example, does a large value for one of the variables tend to occur with large values of the other variables? Are there statistically significant differences between survivors and non-survivors for the mean values of the variables? Do the survivors and non-survivors show similar amounts of variation for the variables? If the survivors and non-survivors do differ in terms of the distributions of the variables, then is it possible to construct some function of these variables that separates the two groups? It would then be convenient if large values of the function tended to occur with the survivors, as the function would then apparently be an index of the Darwinian fitness of the sparrows. So these are several very interesting questions, and it's a very nice data set. It's not a large data set. It's not a complicated data set, not a complicated experiment. But it's very interesting, and so that's why I wanted to look at this. So what I want to do, I'm going to show you some analyses that are contained on my server for this class. You don't have access to this yet, but you will hopefully by the end of the week. We're going to be making a lot of use of this website. that I've built specifically for this course. It's not fancy, all right, so please don't don't expect anything really great, but it does contain a lot of information. It's useful for the class. So this is one of the pages that I have for this system, and here we have at the very top, well, you see here that these are selected programs and solutions for data sets from Brian Manley's text. And the very first data set that we have, the body measurements of female sparrows, which we just described. Now, let me show you a description of the variables that are contained in this data set. All right, and so we have, let's see here, 7 variables, I suppose. We have a variable called bird, and this is just a unique identifier for each bird. And then we have response variables 1 through 5. Now, these are continuous type response variables that are at the highest level, the ratio level of the ratio data level. All right. Now, x1 is the total length of the bird. x2 is what's called the alar extent, which is the distance between the tips of the wings fully extended. x3 is the length of the beak and head. x4 is the length of the humerus. And then x5 is the length of the keel of the sternum, the ridge along the breastbone of the bird, to which the flight muscles are attached. And so here we have, I found this on the internet, diagram showing the keel of the sternum. And so the x5 is the length of that keel. And then finally, we have a variable called group, which is a classification variable that identifies whether the bird survived or did not survive. And then we're told that birds in the data set, birds 1 through 21 survived, and the remaining birds, birds 22 through 49, did not survive. Okay, so let me back out of that a bit, and let's take a look at the data set structure. All right, and so we're going to focus on, well, we can see here that we've got 49 observations in the data set. There are 7 variables, as I just discussed. And then down here we see the variable names. We see the type, the SAS type. So the first 6 are numeric variables. And then the 7th is a character variable. That's the classification variable. Although bird is, in this data set, represented numerically, it's really just a nominal level of data. Okay, now let's look at the data themselves. And so here we have a listing of the data set. And so I have my various variables listed here across the top. You can see here that we have this variable bird, which identifies each bird uniquely. And then you can also see that the first 21 birds were survivors, and the rest of the birds were non-survivors. And then you get a sense of the values for the 5 variables, their magnitudes. Perhaps you might get a sense of the variability if you look real close at this. And I believe that the units for all of these variables are millimeters. So they're all measured in the same units. Now, one of the questions was, to what extent are these variables related? And so let's see here, if we go back to, yeah, that was question 1. How are the various measurements related? For example, does a large value for one of the variables tend to occur with large values of the other variables? Now, you'll remember that one of the reasons for using principal component analysis, one of the purposes, is to identify the true dimensionality of a data set. Now, in this data set, we have 5 response variables. Okay, let me get back here. We've got 5 response variables that we're going to be analyzing. And so the data set has 5 dimensions throughout which the data can vary, the data points can vary. So think of each of these observations as a data point in 5 dimensions. And so the data set has 5 dimensions throughout which this set of 49 observations can vary. But now, in many cases, a multivariate data set is not going to vary throughout all the dimensions that it has available to it. And one of the situations where that is going to occur, or one reason for that, is that if the response variables are correlated. And so that is what this first question is getting at. How correlated are these variables? For example, if if we consider, for example, the total length of the bird, if that's large, do we also expect x2, the alar extent, the distance between the tips of the wings fully extended, to be large? Would we expect the length of the beak and head to be large when the total length of the bird is large? Would we expect the length of the beak and head to be small when the total length of the bird is small? Would we expect the length of the keel of the sternum to be large when the length of the beak and head is large, and so forth? So those kinds of questions. To what degree, to what extent are these 5 variables correlated? And if they are correlated, then that would indicate to us that the data, although the data has 5 dimensions throughout which the data points can vary, it may be only varying within 1 or 2 of those dimensions. So one way to start to think about this is to construct a scatter plot of the data. If we look at the raw data, it's very difficult really to discern much looking at these raw values, these raw data values. All right. I mean, we might spend some time looking at them and trying to see, well, for large values of x1, do I tend to see large values of x2? But look, to be honest with you, I can't do that. Maybe you can, but I can't. I can't look at this raw data and tell much of anything. So I need some help. I've got to start processing the data. And one of the ways that we do that is to start looking at graphs of the data. And for this kind of data, perhaps the most helpful type of graphic are scatter plots. And so here I have a scatter plot matrix called a matrix because it's a 1, 2, 3, 4. Well, it's a 5 by 5, right? Because we have 5 response variables. So we have a cell for each each combination of the 5 variables, and those are actually duplicated, right? Because we've got scatter plots above and below the diagonal. All right, but you can see here, for example, that this scatter plot right here, this is a scatter plot of alar extent on the horizontal axis and total length on the vertical axis. And so you can see here that there is in fact an increasing linear trend. All right. In fact, you see an increasing linear trend in virtually all of these plots. And so that tells us that there's quite a bit of positive correlation between these 5 response variables. And so because of that, we would expect that the data are not varying throughout all 5 dimensions. Now, one of the other nice things about this scatter plot matrix, it's been constructed in such a way that down the diagonal, see, it would make no sense to plot a variable against itself. Okay, and so what we've done here is we have created histograms for each of the variables. And so these scatter plots are bivariate plots. The histograms are univariate plots. And so we are able to get a sense of the shape of the distribution of the 5 variables, and also the modality. Again, the modality is the number of peaks. And if you've got more than one peak, that could indicate more than one subpopulation. And so you see here in the first histogram for total length, we do have a bimodal histogram. And so this may correspond to 2 groups, but perhaps the survivors and non-survivors. Who knows? It would take more analysis. And then you see for the rest, we have unimodal histograms. And there tends to be some skewness in most of these, but perhaps not a whole lot. And if you remember back to your first 2 methods classes, it's always good to look at your data. You want to get a sense of the shape of the distribution of your data, in particular the modality and also the symmetry or lack of symmetry In other words, skewness. Right? So if there is skewness, how much skewness is there, and so forth. So this is a good start to looking at the data. This plot was constructed in SAS, and we'll see how to do that using SAS as well as Enterprise Guide. And so again, beginning our analysis of this data, the data are correlated, and we expect we expect the data to not, we expect to be able to reduce the dimensionality of the data set. That's the bottom line. Now, to what extent can we reduce the dimensionality? Well, that's going to require doing the PCA, the principal component analysis. And I've done two principal component analyses here, one using the raw data and one using the standardized data. And we'll talk about why it might make sense to analyze standardized data at some point, very soon. And we'll look at both of these today in this lecture. But let's start off by looking at the analysis, this analysis here. In fact, what I'm going to do, I'm going to bring up SAS, and I'm going to run the analysis. I'm going to show you the program, and I'm going to post this program on Moodle so that you can download the program and run it yourself in SAS. Okay, so here is SAS, and I have a template here that I've used, a SAS programming template, and this template is going to be available to you it's not on the Moodle, it's going to be available to you on my course website, which you'll have access to hopefully by the end of the week. And within that template, you will be adding the code that you need to run your analyses. Now, there are some SAS statements that you really ought to have in every program, and I call them housekeeping statements, and I've got those listed up here. And so those are going to be in the template. You're not going to have to type those. Then I have an information block up here, and this is all commented out, so SAS doesn't care what's in here. All right, but we can use this and to identify, for example, if you're writing a SAS program for an assignment, you can put in the assignment number. You can tell me which team you're on. We're going to be forming teams here very shortly, and who the authors are. And then I've also got some information here. For example, if you are using a SAS program from somewhere else, and this might be most applicable in the context of the poster project. If you're using somebody else's SAS code, if you've downloaded some SAS code from somewhere on the internet, just make sure that you cite that. This is information here that you could include. We're not going to focus on that right now. We're going to focus on how to do the principal component analysis for this data set. And let me also show you. Let me go back to the web page, the website on my server for this course, and let's see here. Let me back out of here, and this is the main page for the web course. Again, as you can see, it's not fancy, right? But the course data, the data that we'll be using for this course, is available here on this website, and here under datasets for the Manley text. Here we have all the data sets that we have available to us from that book. And so here is the data for table 1.1, the body measurements of the female sparrows, in various formats. I've got it in the Excel spreadsheet format, in the ODS, which is the generic spreadsheet format, a CSV file, and also for a SAS data set. And so you'll be able to download these. Might be best just to download the SAS data set and then read that into your SAS program, which I'll show you how to do in just a second. Let's see here. Let me get back to the SAS program. So this is the code that I'm using to analyze the data. Now, the first thing I do, I have to create what's called a libref. It's a reference to a SAS library, and a library is just a directory or folder on your computer where a SAS dataset resides. And so all we're doing is replacing this long uh, path here with an abbreviation for that. And then we'll use that abbreviation down here in the data statement, which tells SAS where to look for that data and to create a temporary version or a temporary copy of that data set. And while I'm talking about that, let me just say a word or two about that. Again, I always use a temporary version of a data set. I never, or at least almost never, work directly with the actual data sets that have been created and stored. And I think that's a habit I got into when I was working in industry, in the pharmaceutical industry. A lot of time and effort goes into creating the data sets that pharmaceutical companies use to obtain results. And there's a lot of man hours involved in that. And so you would never, ever run your net. You would never get in and start modifying the actual data set. For example, for a clinical trial, you'd always create a copy of that, like I'm doing here, and then analyze the copy. You never want to risk messing up the data set. So that's what I'm doing here. The data statement says create a data set. And so it's going to create a temporary version of the table 0101 data set that is in the directory pointed to by that libref. Okay? And then I'm going to, just to make sure that I've connected to that data set and created the temporary version correctly, I'm going to print a listing of the data set and just look at it and make sure that I've got the right data. And then the SAS code to do the principal component analysis is very, very short, right there. Okay? You can see there's not much we have to do this principal component analysis in terms of SAS programming. All of the analysis requirements or capabilities are encapsulated in this particular proc, this procedure. Okay, so let's go ahead and run this. And then again, we run this by clicking on the submit button, or the running man button. And so let me do this. And so you see here that we got results. Let me go back to my log just to make sure that I don't see any red, I don't see any error messages. It's always good. You always want to check your log to make sure there are no error messages, which would be red. If you see any green, those are warnings. You need to see what those warnings are telling you, but typically you can proceed as planned if you don't have any red. Okay, so here we have the results, and let me just start off. We're looking at the listing of the data set, and so we see that we do have we've connected to the data set, created a temporary version, all right, and we do have the data we need. We've got the variables we need. We've got all the observations we need. Okay, and then scrolling up. Okay, so in my titling, I've indicated that I'm analyzing the unstandardized variable. So I'm analyzing x1 through x5 directly. And so proc printcom is going to first give us some summary statistics. It's giving us the number of observations in the data set, 49 observations. It's giving us 5 variables. The number of variables, the number of response or analysis variables that we're using in the analysis. And so we're using x1 through x5, so there are 5 of those variables. It then gives us univariate statistics, the basic univariate statistics for the 5 variables. So it gives us the sample mean for each of the 5 variables, and it gives us the sample standard deviation. Now, one of the things we want to look at are the magnitudes of the standard deviations. And in some cases, if there's a wide disparity, we may want to consider analyzing not the unstandardized data, but the standardized data. And what that would do is put all of the variables on an equal footing with respect to or from the perspective of the principal component analysis. Now, that's going to be most important, I think, in my opinion at least, when the data are measured with different units. But in this case, the data all have the same units. They're measured, these are lengths in millimeters. And so for that reason, even though there's a bit of disparity in the magnitudes of these standard deviations, I don't have an issue using the unstandardized data as input to this principal component analysis. But we actually are going to look at how to do, we're going to look at this analysis on the standardized data as well. And we can then compare results. Okay, so then in addition to these simple univariate statistics, then we have some bivariate statistics, and in particular, we have the sample covariances. So this is the estimated covariance matrix. This is cap sig hat. Okay. Now down the diagonal entry, down the diagonal of this matrix, okay, these are the estimated variances for my 5 variables, and then the off-diagonal elements are the estimated covariances between the variables. So it is this matrix, this sample covariance matrix, that is the object of the analysis. SAS proc princom is going to extract the characteristic roots and the length 1 characteristic vectors of this estimated matrix, this sample covariance matrix, which again is an estimate of the true but unknown population covariance matrix. Now, the characteristic roots are given in this table here, the eigenvalues or characteristic roots of the covariance matrix. Again, characteristic roots are also called eigenvalues. That's, in fact, eigenvalues is probably the more prevalent term. Okay, so these, for a 5x5 sample covariance matrix, or for a 5x5 symmetric matrix in general, there are 5 characteristic values. And so we see here in this first column we have the characteristic values. In the next table we have the 5 length 1 characteristic vectors of this sample covariance matrix corresponding to the 5 characteristic roots. Okay, and so in each column we have the estimated characteristic vector. Now remember that the entries in the characteristic vector are the coefficients which are multiplied against the original variables. So I have the original variables here, x1 through x5. And so to get the first principal component, I'm going to multiply these coefficients against the variables and add them up. To get the second principal component, well, I'm not going to do it, SAS is going to do it. And so to get the second principal component for each bird, SAS is going to take these coefficients, multiply by the corresponding variables, and add those up. And so on for the rest of the principal components. Now remember that the characteristic roots, the eigenvalues, these are the variances of the principal components, the estimated principal components, okay, for these data. So like I said when we were talking about principal component analysis and the fact that the solution to the principal component problem is a characteristic root and characteristic vector solution, I indicated when we talked about this in a previous lecture that I'm not going to have you extract characteristic roots and characteristic vectors. We're going to let SAS do that for us. And so you can see here that SAS, we've instructed SAS to do the analysis for us. It has taken the data, those 49, that random sample of 49 response vectors, okay, 5x1 response vectors measured on each of the 49 birds. It's calculated the sample covariance matrix. From that covariance matrix, it has extracted the characteristic roots and the length 1 characteristic vector. So it's doing that for us. We don't have to do it. We just have to know how to use it and how to interpret. Okay, now, one of the things we talked about in the previous lecture is how many principal components should we use? Remember that one of the goals of principal component analysis is to determine the true dimensionality of a data set with the idea of reducing the dimensionality of the data set if it's possible, if it's appropriate. And so we said that one of the criterion that we can use is to select the number of principal components that account for a certain proportion of the total variability in the original data set. Now, if we go back up here, remember that the total variability for a distribution or a data set is the trace of the covariance matrix. It's the sum of the variances, all right, in that covariance matrix. Now, the good thing is we don't have to, I mean, we can see these estimated variances, and we can add those up with a calculator, but the good thing is we don't have to. SAS has already done that for us, and so the total variability is about 40.97. So that's the total variability of these 5 variables in this data set. Now, so how many, and again, these are the variances of the principal components. So how many principal components would we need, for example, to account for at least 80% of the total variability in the data set? Well, these cumulative proportions are given in this column here. So we can see here that the first principal component accounts for 86.22% of the total variation in the original data. And 2 principal components accounts for 97.51%. And so you can see here that if we were going to use a threshold of 80%, we would only need to use 1 principal component. I would probably pick 2 for a couple reasons. Number one, if I pick, I can still create nice plots. I can still plot 2-dimensional data. So there's no reason not to use 2 principal components from that perspective, at least. Now, the other reason I might use 2 is when I look at the scree plot, remember that what we're looking for is we're looking for the elbow. Where does this thing really start to level off? And this is actually a really nice data set for showing this, because it really does level off when you get to this 3rd principal component. And so if you'll remember, my recommendation was, and I think it's really the common recommendation, if you have a nice elbow like this, find the elbow and then back up 1. And for that reason, I would probably go, based on this scree plot, I would use 2 principal components. Now, the other really nice thing that SAS provides is the scree plot, but with the cumulative proportions. And so the first principal component accounts for a little over 80% of the original, or of the variability in the original data set. And then there's some additional variation that's accounted for, and they're showing these accumulated proportions. And so essentially, this plot here is a plot of these values in that 4th column. So again, the recommendation would be to use either 1 or 2 principal components for summarizing this data. Now, one of the things that you can use principal components for is to identify outliers in your data set. Identifying outliers is important in any situation, and it can be difficult in many situations, but it becomes quite difficult with multivariate data sets, because the data have so many dimensions throughout which they can vary. And so, how can you get a good visual of that? Because a lot of these techniques where we are identifying outliers, we're doing it visually. We're creating various kind of graphics. Well, we've got 5-dimensional data here. How do you plot 5-dimensional data? Well, because principal component analysis is able to, at least in this case, we're able to reduce the dimensionality of the data set. We're able to account for 97.51% of the total variability in the 5-dimensional data using only 2 dimensions. And so this is going to be very helpful in trying to identify outliers. So such a plot is not included with the current program that we have, but I'm going to go in here and I'm going to remove some of the comment symbols there. So now, I'm going to rerun this, and so now we're going to get a whole lot of output actually, a whole lot of graphics. We're not going to look at all these. Now, what we're going to focus on right now is looking at a scatter plot of the principal component score. So this is called the component scores matrix. It's a scatter plot matrix, but it's not a scatter plot matrix of the original data. It's a scatter plot matrix of the values of the principal components that SAS has just computed based on this principal component analysis. And so now there are several things we want to look for in this component score matrix. We want to look at these scatter plots and see if we see any observations, if we see any birds that appear to be different from the rest. So are there any outliers with respect to these plots? Now what we ought to be seeing in each of these plots is a circular or elliptical pattern of points. Remember that by convention, the 5 principal components are all pairwise uncorrelated. So we're not going to see any kind of a linear trend in these plots. We're going to see, either somewhat circular types of plots, or perhaps a little bit elliptical. But actually, we really shouldn't even see much elliptical either. So, but what we are looking for are outliers. And so, it looks like perhaps this one might be an outlier, maybe that one. So we might have a small number of outlying birds. From this perspective, it looks like that bird might be somewhat different than the rest. And that that when we see something like that, we want to go back to the original data, make sure that the data are correct. So that may force us to go back to lab notebooks or the original data sources to make sure that the data have been input correctly. The other thing we want to look for here, we do want to look at these histograms, because if the original data are multivariate normal, then the principal components will also be multivariate normal. You'll remember that from the last lecture we did. And so, and then on top of that, if the principal components are in fact multivariate normal, then each individual principal component will be univariate normal, right? So we gave those results in the previous lecture. And so what we want to do is look here at these histograms. If we see histograms that look very non-normal, then that could be an indication that that particular principal component is not normally distributed. And if any of the principal components are not normally distributed, that implies then, that necessarily implies that the original data are not multivariate normal as well. So this type of plot is going to allow us to, number one, take a look and search for outliers, and it's also going to allow us to begin to look for violations of underlying assumptions that many of the multivariate analyses are based on, such as multivariate normality. Okay, so that is all. There are plenty of other plots. We're going to get into those plots. Before we do, we need to talk some more about some of the some conceptual, and perhaps we might call it theoretical results, but just to understand where these subsequent results down here come from, we need to talk a little bit more about that first. So I think that this is probably a good place to stop this video. Again, I am going to post this program on Moodle, and so you'll be able to download this program and run it in SAS yourself. Well, you won't be able to do it until we post the data sets out there. but very soon you'll be able to do this analysis yourself in SAS.